Welcome back. Let's look at some example problems involving planes in 3D space. Alright, so here's our first example. We want to find an equation of the plane passing through the point 1, 3, negative 7 and is perpendicular to the vector n, which is the position vector of the point 2, 3, 4. Okay, so when you want to find an equation of a plane in 3D space, you need two things. You need a point in that plane, which we have right here, and we need a vector that is perpendicular to that plane, which we have right here. We call that a normal vector. All right, and so in this example, we have been given both things that we need to find the equation of a plane. And so in order to set up that equation, it's helpful to know the standard form of the equation of a plane in 3D space. It looks like this. We have a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. All right, now the values a, b, and c are the components of the normal vector, or the vector that's perpendicular to the plane, and the values x1, y1, and z1 are the coordinates of the point in that plane. Okay, so in this case, x1 is the x-coordinate of the point, which is 1, y1 is the y-coordinate of the point, which is 3, and z1 is the z-coordinate of the point, which is negative 7. Okay, and then for a, b, and c, a is the x-component of the normal vector, which is 2, b is the y-component of the normal vector, which is 3, and c is the z-component of the normal vector, which is 4. All right, so in general, a normal vector to a plane has components of a, b, and c. And so in this case, a is equal to 2, b is equal to 3, and c is equal to 4. Okay, I think it's always helpful to write down what a, b, and c are in a problem like this. That way you are less likely to make a mistake and accidentally use the coordinates of the point as the values of a, b, and c, which you don't want to do. That's the worst kind of mistake that you can make in these problems. You want to make sure that you correctly identify the values that make up this equation of a plane. But now that we have those values of a, b, and c identified, and we know that the coordinates of this point make up x1, y1, and z1, we can set up an equation for this plane. And so let's do that. We're going to start with a times x minus x1. So we will have 2 times x minus 1, right? That's our value of x1, the x-coordinate of our point. Then we will add that to b times y minus y1. So we'll have 3 times y minus 3. So I'll write down 3 times y minus 3. And then we add that to c times z minus z1. And c is equal to 4, so we'll have 4 times z minus negative 7. All right, so we have 4 times z minus negative 7, and that's equal to 0. Don't forget that last part of the equation. It is important. All right, and so this would be the standard form of an equation of this plane, but we typically want to simplify it. We want to get it into its simplest form. And so what we should do is multiply 2 by x minus 1, multiply 3 by y minus 3, and multiply 4 by z minus negative 7. And then we can simplify from there. So if we do that, we'll have 2x minus 2 plus 3y minus 9 plus 4 times z, and then we have z minus negative 7, right? So that would be the same as z plus 7. So I'm going to rewrite this to be z plus 7, and so then 4 times 7 is 28. So we have plus 28, and that's equal to 0. And now we can simplify this further. What we want to do now is separate our variable terms from our constant terms. All right, our variable terms are the terms involving x, y, and z. We want to keep them on this side of the equation and then move over the constant values of negative 2, negative 9, and 28 over to the other side of the equation. And by doing that, we will create the general form of an equation of this plane. All right, in other words, our equation is going to look like this. We will have a times x plus b times y plus c times z, which will be equal to some constant value d, which we will get after moving those constant values over to the other side of the equation. Okay, so this right here was the standard form of the equation of a plane, And this right here is the more simplified form, which we refer to as the general form of the equation of a plane. Okay, but now let's get this equation in this form. We want to move -2, -9, and +28 over to the other side of the equation. So we will add 2 to both sides of the equation, add 9 to both sides of the equation, and subtract 28 from both sides. So if we do that, we'll have 2x plus 3y plus 4z, and that will be equal to 2 plus 9 minus 28. All right, now 2 plus 9 is 11, and then 11 plus -28 will give us -17. So we will have 2x plus 3y plus 4z is equal to -17. And that right there is an equation of the plane passing through this point and is perpendicular to this normal vector. Okay, this is an equation of that plane in the general form. And you can see that this does match up with this right here. We have a times x, right? A was equal to 2, so we have 2 times x, and then we have plus b times y. B was equal to 3, and we have plus 3y, and then we have plus c times z, and c was equal to 4, so we have 4z, and that's equal to some constant value d, which in this case is -17. Okay, and so that's how we find an equation of a plane given a point that's on that plane and a vector that it's perpendicular to. And so with that, let's take a look at another example. Okay, so next up we have a very similar example. Once again, we want to find an equation of the plane that passes through the point 0, -1, 4 and is perpendicular to the vector n, which is the position vector of the point -1, 5, -6. Okay, so we have the same exact problem as we did last time, except now we have a different point and a different normal vector. And so we have everything we need to set up an equation of a plane, and so we can get right into it, right? We have a point on the plane and a vector perpendicular to the plane, which is all we need to set up an equation of that plane. And so let's do it. First of all, we want to identify the values of a, b, and c, or the components of our normal vector. And so in this case, a is equal to -1, b is equal to 5, and c is equal to -6. A is the x component of the normal vector, b is the y component, and c is the z component. All right, so let's set up our equation here. Let's set up the standard form of an equation of the plane. We want to find a times x minus x1, right? Now a is equal to -1, so I'm going to rewrite that to be -1 multiplied by x minus x1, but x1 is the x-coordinate of our point, which is 0. So I'm going to erase x1 and write 0. Then we will have plus b times y minus y1, but now b is equal to 5, so let's rewrite that. B is equal to 5, and then y1 is the y-coordinate of our point, which is a -1. So I will erase y1 and write -1. And I'm going to need more space here, so I'm going to move these numbers a little bit. And the next part of our equation will be plus c times z minus z1, and c is equal to -6, so let's replace that. In fact, we can just write -6 times this quantity, so we will have -6, and then z1 is the z-coordinate from our point, which is 4, so I will replace z1 with 4. Okay, and then don't forget to write equals 0 to finish off that equation. All right, so this is the standard form of an equation of this plane. Now what we want to do is simplify it and get it into the general form. And first things first, notice that we have y minus -1 right here. That would be the same as y plus 1. So I'm just going to rewrite that here. We'll have y plus 1. And then all we have to do to simplify is distribute -1 through this quantity, 5 through this quantity, and then 6 through this quantity, or I guess -6 through this quantity. And so if we do that, we will have -x, and then plus 0, plus 5y plus 5, and then minus 6z plus 24, and that will be equal to 0. All right, and so now what we want to do is keep all of our variable terms on one side of the equation and move all of the constant terms over to the other side. Okay, so in this case, the constant terms are 5 and 24. I'm not really worried about this 0 because it's just 0. We don't really need to have that there anyway. Adding 0 does not affect this equation in any way, so what we have to do here is subtract 5 from both sides of the equation and subtract 24 from both sides of the equation. And so if we do that, we will have negative x plus 5y minus 6z, and that will be equal to negative 5 minus 24, and negative 5 minus 24 is negative 29, so our final answer is negative x plus 5y minus 6z is equal to negative 29. That is an equation of the plane passing through this point and is perpendicular to this vector. Okay, and now before we look at the next example, I do want to quickly mention this. Notice that in these examples, the directions say to find an equation of the plane, not the equation. And what that means is that there's not just one correct equation of any plane. There are a bunch of different equations that would represent the same plane. It all depends on the normal vector that you use, right? If you think about it logically, there's not just going to be one normal vector for any plane. There are a lot of different vectors that are perpendicular to any plane. All of them would be parallel and have the same direction, but those different normal vectors would be scalar multiples of each other, and so they could look a little bit different than what we have right here. Okay, so if we were given a different normal vector that was a scalar multiple of this one right here, it would still be perpendicular to the plane, but it would give us a different equation for that plane. Okay, so I just wanted to quickly explain that. There is a reason why these problems ask you to find an equation of the plane and not the equation of the plane. There are a lot of different equations that could represent any particular plane within 3D space, but in these problems they are usually looking for one specific equation based on the normal vector that you're given. So just be aware of that. There's usually a pretty obvious equation that they want you to find, but if you used a scalar multiple of this normal vector, your equation might look a little bit different, but it would still be correct. Okay, so that's just something that you want to keep in mind going forward. But with that, let's take a look at a slightly different example. Okay, so next up we want to find an equation of the plane passing through the point 322 and is perpendicular to the line x minus 1 divided by 4 is equal to y plus 2 is equal to z plus 3 divided by negative 3. All right, so this is a little bit different than what we've done so far. In our previous two examples, we were finding an equation of a plane given a point on that plane and a vector that was perpendicular to it, or a normal vector, but in this case we're given something a little bit different. We still have a point on the plane, that part didn't change, but now we are given a line that the plane is perpendicular to. All right, so if I draw a quick sketch of what's going on here, we're looking at a plane that might look like this, and we know that there is a line that passes through that plane at some point, and that line is perpendicular to the plane. All right, and so what we need to do is determine how to represent this plane given this point and this line with an equation. And so how are we going to do that? Well, remember, you always need to have two things to find the equation of a plane in 3D space. You need a point on that plane, we have that, and we need a normal vector, a vector that is perpendicular to that plane. And that's what we don't have right now, right? We need that normal vector, okay? That's always going to be your goal in these problems. If you're not given that normal vector, you got to find a way to get it. And so in this case, how do we get that normal vector from this line? Well, remember what the equation of a line is composed of. What did we need to find the equation of a line in 3D space? Well, we needed a point on that line, and we needed a direction vector, or a vector that is parallel to that line, a vector that describes the line's direction. So, what that means is that in this equation, we could pull out a direction vector that is parallel to this line, and if that vector is parallel to this line, that means that that vector would also be perpendicular to the plane, just like the line is, right? This line is perpendicular to the plane, so its direction vector must also be perpendicular to that plane. So what we want here is the direction vector from this line, and that will be our normal vector. That will be the vector perpendicular to our plane. And so how do we get that direction vector? How do we find the vector parallel to this line? Well, what we're given here is a symmetric equation of the line. And so if you remember the general form of the symmetric equation of a line, it looks like this. You have x minus x1 divided by a, and that's equal to y minus y1 divided by b, and that's equal to z minus z1 divided by c. Right, you're subtracting the x, y, and z coordinates of a point on that line from x, y, and z, and then you're dividing each of those parts by a, b, and c, which we call direction numbers. They are the components of the direction vector that is parallel to that line. So in this case, the direction vector for this line will have components of a, b, c, which are just the values in the denominator of each part of the symmetric equation. So if we look at our given line here, or this given symmetric equation, what is in the denominator of each part? Well, we have 4, and then for this middle one, you could rewrite it to be y plus 2 divided by 1, right? Anything divided by 1 is itself. So we'd have 1 and then negative 3. A is 4, B is 1, C is negative 3. So our direction vector for the line, vector v, is equal, and I should have equal signs there as well. I don't know why I didn't write that the first time. Anyway, our vector will have components of 4, 1, and negative 3. This is the vector that would be parallel to this line. And so we could draw that here. We could have a vector like this. That would be our direction vector, vector v, and that vector would also be perpendicular to the plane. So not only is this vector a direction vector for this line, but it's also a normal vector for this plane. So really what we can write here is that the normal vector is equal to the vector with components 4, 1, and negative 3. It's the same exact vector as the direction vector for the line that is perpendicular to our plane. Okay, and so now we have everything that we need to find an equation of the plane in this example. We have a point on the plane and we have a normal vector. So let's set up an equation for this plane. We'll have a, which is 4, times x minus x1, the x coordinate of our point, which is 3. So we have x minus 3, and then we will add b, which is 1, times y minus y1, which is the y coordinate from our point, and that's 2. So we have y minus 2, and then we're adding, or in this case, I guess we would subtract 3 because we have negative 3 as our value of c. So I'll write it like this. We'll have minus 3 times z minus z1, which is the z coordinate from our point, and that's 2, and that will be equal to 0. Okay, now if we simplify, we'll have 4x minus 12 plus y minus 2 minus 3z plus 6 is equal to 0. And so now what we want to do is move those constant values over to the other side of the equation. So that will be negative 12, negative 2, and positive 6. So we're going to add 12 to both sides of the equation, add 2 to both sides of the equation, and subtract 6 from both sides of the equation. And so what we'll be left with is 4x plus y minus 3z is equal to 12 plus 2 minus 6. All right, 12 plus 2 is 14, minus 6 is 8. So I'm just going to erase that, and we will have 8 on that side of the equation. And so what we're left with here is an equation of the plane passing through this point and is perpendicular to this line. Let's take a look at another example. Okay, so for this example, we want to find an equation of the plane passing through the point 10, negative 2, 7, and is parallel to the plane 5x minus 3y plus z equals 4. All right, so once again, we have another variation of these problems where we want to find an equation of a plane. This time, once again, we are given a point on that plane, but the second thing that we're given is a little bit different. We're not given a vector perpendicular to the plane, and we're not given a line perpendicular to the plane. We are given another plane that the plane is parallel to. And so once again, let's draw a picture of what's going on here. We're going to have one plane that we want to find, and then we have a second plane that is parallel to that plane. And so how are we going to use that other plane to help us represent this plane with an equation? It's not initially clear how we can do that, but if you ever get stuck in a problem like this, you just have to remember what you need to represent this plane. What are the two things that you need to find an equation of a plane? You need a point on that plane, and you need a normal vector, a vector perpendicular to that plane. And so how would we find that normal vector in this problem? Well, you might have been able to guess that it's going to involve using this other plane that we've been given. I think that part is at least obvious, but how would we use this plane to find a normal vector to this plane? Well, since we are given the equation of this plane parallel to the plane that we want to find an equation for, we can actually determine what the normal vector for this plane would be, right? Remember that the general form of an equation of a plane is a times x plus b times y plus c times z, and that's equal to 0. And a, b, and c are the components of the normal vector for that plane. So in this case, a is 5, b is -3, and c is 1. That's the coefficient of z. So the normal vector for the plane that we've been given would have components of 5, -3, and 1. And so that is the normal vector for this plane that's parallel to the plane that we want to find an equation for. And so that vector might look something like that. It's perpendicular to the plane. And so that's good and all. That's helpful to know. But how do we use that normal vector to find a normal vector for this plane that we want to find the equation for? Well, if we think about it a little bit, this plane that we're given is parallel to the plane that we want to find an equation for, which means that if this vector is perpendicular to this plane, then it would also be perpendicular to this plane, right? If the two planes are parallel, then their normal vectors would be parallel as well. A vector perpendicular to this plane would also have to be perpendicular to this plane since they're both parallel. And so what we can do here is simply just use the same normal vector from the plane that we've been given for the plane that we want to find an equation for. All right, so let's use that normal vector and this point to find an equation of the plane in this example. Remember that from our normal vector, we get the values of a, b, and c. I'm just going to write those down really quick. A is equal to 5, b is equal to -3, and c is equal to 1. And so now let's set up our equation. We're going to have a, which is 5, multiplied by x minus x1, the x coordinate from our point, which is 10. So we have x minus 10, and then we'll add b, which is -3. So I'm going to write -3 here. We'll have -3 times y minus y1, and y1 is -2. So we have -2. And then we will add that to c, which is 1, multiplied by z minus z1, the z coordinate from our point, which is 7. So we have z minus 7, and then that's equal to 0. All right, now if we simplify, first of all, y minus -2 is the same as y plus 2. So I'm just going to rewrite that, and we'll have y plus 2. And then let's just multiply a, b, and c through each of their respective quantities. So we'll have 5x minus 50 minus 3y minus 6 plus z minus 7 is equal to 0. And so now, to finalize this equation, we want to move all of our constant values over to the other side of the equation. So that would be -50, -6, and -7. We're going to add 50 and add 6 and add 7 to both sides of the equation. And so if we do that, we'll have 5x minus 3y plus z is equal to 50 plus 6 plus 7. And 6 plus 7 is 13, plus 50 is 63. So I'm just going to erase this and write 63. Okay, and so that right there is an equation of the plane passing through this point and is parallel to this other plane. Okay, you'll notice that both of these plane equations look the same on the left side of the equation, right? We have 5x minus 3y plus z right there and right there. The only difference in the equations is the value that they are equal to. All right, this one is 4, and this one is 63. Let's take a look at a different example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. All right, so next up we want to find an equation of the plane passing through the points 1, 2, 3, 3, 2, 1, and -1, -2, 2. All right, so this is a little bit different once again. This time, instead of being given 1 point and a vector perpendicular to the plane, or a line perpendicular to the plane, or another plane parallel to the plane, we're just given 3 points, which at first, if you've never seen a problem like this before, doesn't seem like enough information. It doesn't seem possible to find an equation of a plane using just 3 points. But it is possible. In fact, it's actually a pretty cool process. If you watched my lesson video on this topic, then you know how we go about this. But I'm just going to explain the process again in case you've never seen it before. If I draw a picture of what's going on here, let's say our plane looks something like this. We want to find the equation of this plane, and we're given 3 points that it passes through. So that could be a point here, here, and here. How could we use those 3 points to find an equation of that plane? And once again, if you're ever stuck in a problem like this, you always want to fall back to that same question. What 2 things do I need to find an equation of a plane? And those 2 things are a point on that plane, and we have 3 of those. That's good. We can check off that box. But then we also need a normal vector, a vector perpendicular to that plane. And so that's what we have to find here. Somehow we have to use these 3 points to find a normal vector, a vector perpendicular to the plane. And so the way we do that is to actually create 2 vectors using these 3 points, right? So those vectors might look like this and this. We find 2 vectors by using those 3 points. And so those 2 vectors would be within that plane. They would be parallel to the plane. And then remember, if you take the cross product of 2 vectors, the result is a vector that is perpendicular to both of those vectors. And so if these 2 vectors are parallel to the plane, and their cross product is a vector that's perpendicular to those vectors, then that cross product vector will also be perpendicular to the plane. All right, so the cross product of those 2 vectors will give us a normal vector for that plane, a vector that is perpendicular to both of those vectors, and as a result, will also be perpendicular to the plane. Okay, and so let's work on that process. Let's use these 3 points to find 2 vectors, and then let's take the cross product of those vectors to find a normal vector to the plane. And just to make things easier for us to reference, I'm going to label these points. This will be point A, this will be point B, and this will be point C. And so what you want to do is just pick one point to be the initial point of both vectors. In this case, I'm going to choose point A to be the initial point. And so the 2 vectors that I'm going to find here are vectors A, B, and A, C. Okay, and so let's work on finding these. Remember that to find a vector in component form using 2 points, you want to subtract the coordinates of the initial point from the coordinates of the terminal point. And so we're going to be subtracting the coordinates of A from B for this vector, and then for this vector, we will be subtracting the coordinates of A from C. All right, but let's start with vector AB. We will have 3 minus 1 for the x component. That will give us 2. Then we will have 2 minus 2 for the y component, which is 0. And then we will have 1 minus 3 for the z component, which is negative 2. Then for vector AC, we will have a negative 1 minus 1 for the x component. That will be negative 2. Then for the y component, we'll have negative 2 minus 2, which is negative 4. And then for the z component, we will have 2 minus 3, which is negative 1. Okay, and so those are our 2 vectors that we found that are contained within this plane, these 2 vectors right here. Now what we want to do is take their cross product, and that will give us a normal vector to this plane. And so let's do that. First thing I'm going to do here is just make these 2 vectors a little bit easier to refer to. Instead of writing vector AB and vector AC every time, I'm going to refer to these as vector B and vector C, just to make things a little bit easier for myself. So what we're going to be doing here is taking the cross product of vector B and vector C, and that will look like this. We're going to set up a 3 by 3 matrix that we will then take the determinant of. And if you're not familiar with this process, if you don't know how to take a cross product of 2 vectors, be sure to check out my lesson on this topic where I explain it in more detail. And I would definitely recommend that if you've never seen it before, because I am going to go through the cross product pretty quickly here. The first row of the matrix are the standard unit vectors I, J, and K. The second row will be the components of vector B, and the third row will be the components of vector C. So we'll have 2, 0, negative 2. Those are the components of this vector right here, vector B. And then we will have negative 2, negative 4, negative 1, which are the components of this vector right here, vector C. All right, now to find our cross product vector, or the normal vector, we'll start by looking at vector I here in our 3x3 matrix. I'm going to cross out the row and the column that it's in, and then calculate a 2x2 determinant using the remaining 4 values. So we'll have 0 times -1, which is 0, minus -2 times -4, which is positive 8. So we have 0 minus 8 times I, and then we subtract that second term, which will be multiplied by j. And so we look at j in the 3x3 matrix, cross out the row and the column that it's in, and use the remaining 4 values to calculate a 2x2 determinant. We'll have 2 times -1, which is -2, minus -2 times -2, which is positive 4. So we have -2 minus 4 times j, and then we're adding the last term, which will be multiplied by vector k. And we'll look at k in the matrix, cross out the row and the column that it's in, and then calculate a 2x2 determinant using the remaining 4 values. So we'll have 2 times -4, which is -8, minus 0 times -2, which is 0, and so we have -8 minus 0. Okay, now if we simplify, this right here will just become -8i, so this is equal to -8i, and then we are subtracting -2 minus 4 times j. This will be -6j, but then we're subtracting it, so that becomes positive 6j, and then we're adding -8 minus 0k, which will just be -8k. So we have minus 8k. All right, and so what we have right here is a vector that is perpendicular to both vector b and vector c, or vector ab and vector ac, two vectors in our plane, and so this cross product vector is also a normal vector for this plane. Okay, and so we would call this our normal vector. The value of a, or the x component, is -8, the value of b, or the y component, is 6, and the value of c, or the z component, is -8. And so we can use those values of a, b, and c, along with one of these points on the plane, to find an equation of that plane. In this case, we have 3 different options. You can pick any point you'd like to create the equation of this plane, but I'm just going to pick the first one here, which is point A. I'm going to use an x-coordinate of 1, a y-coordinate of 2, and a z-coordinate of 3, along with this normal vector to create an equation of this plane. And so let's do that next. We're going to have a, or in this case, -8, times x minus x1, or the x-coordinate of the point that we're going to use. Once again, I'm using point A here, so we will have an x-coordinate of 1. So we have x minus 1, and then we're adding that to b, which is 6, times y minus y1, or the y-coordinate of our point, which is 2. So we have y minus 2, and then we're adding that to c, which is -8. So I'm going to write -8 times z minus z1, or the z-coordinate of our point, which is 3. So we have z minus 3, and then that will be equal to 0. And now if we simplify, we will have -8x plus 8 plus 6y minus 12 minus 8z plus 24 is equal to 0. And so now, if we move our constant values to the other side of the equation, we will subtract 8 from both sides, add 12 to both sides, and subtract 24 from both sides. And that will leave us with -8x plus 6y minus 8z is equal to -8 plus 12 minus 24. And -24 plus 12 will be -12 minus 8 will give us -20. So I'm just going to erase this, and we will have -20. And so that right there would be an equation of the plane passing through these 3 points. That is how you would find the equation of a plane when you're only given 3 points that are on that plane. Okay, and one more thing, you could simplify this equation further if you wanted to. Notice that all of the terms in the equation are divisible by 2, so you could reduce it a little bit by dividing each term by 2. If you did that, you would have the following equation of -4x plus 3y minus 4z is equal to -10. That would also be a correct answer if you like to reduce your equations. Okay, and you could change it up even more if you wanted to. You could divide all the terms by -1, and that would make it look a little bit nicer as well, but you don't have to do that. It's totally up to you how you want to simplify or reduce that equation. Okay, but with that, let's take a look at one more example of finding an equation of a plane, and then we'll take a look at some examples of sketching planes in 3D space. All right, so for this example, we want to find an equation of the plane passing through the point 2, 2, 1 and negative 1, 1, negative 1 and is perpendicular to the plane 2x minus 3y plus z equals 3. All right, so this is probably the most complicated example in this video. This example has the most things going on here. We still want to find an equation of a plane, but this time in order to find that equation, we are given 2 points on the plane and then another plane that's perpendicular to it. And I want you to be careful here. This is different from an example we had earlier in this video where we were given a plane that was parallel to the plane that we want to find an equation for. This time the plane that we've been given is perpendicular, so you can't just simply take the normal vector from this plane and assume that it will be the same normal vector for this plane. Okay? Only parallel planes share the same normal vector, not perpendicular planes. So this is a little bit of a different example. And so once again, let's draw a picture of what's going on here. We'll say that the plane that we want to find is this plane right here, and we're given another plane that's perpendicular to it. So I'll say it looks like that. They're going to have some type of intersection where that angle is a right angle. And for this plane that we've been given, we could find a normal vector for that plane. It would be the vector with the components of the coefficients of x, y, and z from this equation. So the normal vector for that plane would look like this. It would have components of 2, negative 3, and 1. And so that vector would look like this. It's a vector that is perpendicular to that given plane. But now that is not the normal vector for the plane that we want to find an equation for, so we can't use that and one of these points to find an equation of that plane. And so once again, we're a little bit stuck here. We have to go back to that same question that I keep bringing up. What two things do we need to find an equation of a plane? Well, we need a point on that plane, and we have two of them right here, so that's good. But then we also need a normal vector, a vector that is perpendicular to that plane, all right? We can't use this normal vector right here. It's not perpendicular to the plane that we want to find an equation for, but rather instead, maybe you've already noticed this, that vector would be parallel to that plane, right? If these two planes are perpendicular, but then this normal vector is perpendicular to this plane, then this vector would be parallel to the plane that its plane is perpendicular to. That was a little bit of a confusing sentence, but the bottom line is that the normal vector of this plane is parallel to the plane that we want to find. And so that normal vector could be contained within this plane. We could move it over right here, and it would be within that plane. Now, in addition to that, we also know 2 points that are in the plane that we want to find an equation for. And so that could be anywhere within the plane. It could be here and here. And so how could we use those 2 points and this vector parallel to that plane to find a normal vector for this plane? Well, it's very similar to the previous example if you watched that one as well. What we can do is find a vector between those 2 points that we've been given, and that vector will be within that plane. It will be parallel to it. And then we would have 2 vectors parallel to that plane, which if we took the cross product of, would give us a vector perpendicular to that plane. All right, the cross product of 2 vectors will always give you a vector perpendicular to both of those vectors. So if this vector is parallel to the plane, and the vector that we make using those 2 points in the plane is parallel to the plane, then those 2 vectors will have a cross product that is perpendicular to the plane. Okay, so we're going to use this vector as one of those vectors in that cross product, and then the other vector that we're going to use we will find by creating a vector between these 2 given points. All right, and so if this is point A and this is point B, then vector AB would be equal to a vector with an x component of -1 minus 2, so we'll have -3, a y component of 1 minus 2, which is -1, and then a z component of -1 minus 1, which is -2. Okay, and so now we have 2 vectors that are parallel to our plane, and so let's take the cross product of them and find that normal vector for this plane. Okay, and then we'll have a normal vector and a point that we can use to find an equation of that plane. Okay, and then just to make this vector easier to reference, I'm just going to call this vector vector B. That'll be easier to work with. And so then what we're going to do here is take the cross product of vector B and vector N, the normal vector for that other plane that we were given. Okay, so let's set up this cross product calculation once again. We're going to set up a 3 by 3 matrix. First row is the standard unit vectors. The second row will be the components of vector b, which are -3, -1, -2. So we have -3, -1, -2. And then the third row are the components of that normal vector that we were given, which has components 2, -3, and 1. So I'll write 2, -3, and 1. And now let's work on finding this cross product vector, or the normal vector for our plane. That will be vector n. All right, that vector will look something like this. It will be perpendicular to the plane and perpendicular to both of those two vectors that are parallel to this plane. And we'll start by looking at vector I in our matrix. We're going to cross out the row and the column that it's in and use these four values to calculate a 2 by 2 determinant. -1 times 1 is -1, and then we will subtract -2 times -3, which is 6. So we have -1 minus 6 times I, then we subtract a value multiplied by vector j, and then we add a value multiplied by vector k. And so let's find those two values, or those two 2 by 2 determinants. Let's look at vector j. We'll cross out the row and the column that it's in and use these four values for a 2 by 2 determinant. -3 times 1 is -3, minus -2 times 2, which is -4. So we have -3 minus -4. And then for vector k, we'll cross out that row and this column, and then use these four values to calculate a 2 by 2 determinant. -3 times -3 is +9, and then we are subtracting -1 times 2, which is -2. So we have 9 minus -2. Okay, and so now if we simplify, I'm going to write it up here. We'll have that the normal vector is equal to -1 minus 6 times I. That will be -7 times I. And then we have minus -3 minus -4 times j. -3 minus -4 will be the same as -3 plus 4, so that will be 1, but then we're subtracting it, so we just have minus j. And then finally we have plus 9 minus -2 times k. 9 minus -2 will be the same as 9 plus 2, so that's 11, which means we have plus 11k. All right, and so that right there is a normal vector for the plane that we want to find an equation for. And so now we have everything we need to find an equation for that plane. We have a normal vector and a point on that plane. In fact, we have 2 points, but I'm just going to use this first one here in our equation. All right, you could choose to use the second one if you wanted to. It doesn't matter. You'll get the same answer either way. All right, and so now let's work on finding that equation. For this normal vector, our value of a is -7, our value of b is -1, and our value of c is 11, right? Those are the coefficients of I, j, and k, the x, y, and z components of that vector. And so using those values, we will have a, which is -7, times x minus x1, the x coordinate from our point, which is 2. So we'll have x minus 2, and then we have plus b, but in this case we have -1, so we'll have -1 times y minus y1, which is the y coordinate of our point, and that's 2. So we'll have 2, and then plus c, which is 11, multiplied by z minus z1, or the z coordinate of our point, which is 1. So we have z minus 1, and that's equal to 0. And now if we simplify, we'll have -7x plus 14 minus y plus 2 plus 11z minus 11, and that's equal to 0. Now what we want to do is move the constant terms over to the other side of the equation. So we will subtract 14, subtract 2, and then add 11. And so what we will have is -7x minus y plus 11z is equal to -14 minus 2 plus 11. And now -14 minus 2 is -16 plus 11 will give you -5. So our final answer, which I am going to write up here, is -7x minus y plus 11z, and then that is equal to -5. And that right there is an equation of the plane passing through these 2 points and is perpendicular to this other given plane. Okay, so that was our last example of finding an equation of a plane for this video. These problems have a lot of different variations. There's a lot of different ways that you can find the equation of a plane given some other information. But if you ever get stuck on one of these problems, just remember you need a point for that plane and you need a normal vector. That is your end goal. You gotta find a vector perpendicular to your plane in some way using the given information. All right, so sometimes there's a little bit of intuition involved with these problems, but if you can draw a picture of what's going on, usually that will help you figure out what you have to do to get that normal vector. Okay, and so now let's look at a couple more examples for this video where we sketch a graph of some planes. All right, so for this example, we want to sketch a graph of the plane and label any intercepts. And our plane equation is 5x plus 12y plus 6z is equal to 60. And so sketching planes in the 3D coordinate system, I would say is probably one of the easiest things you get to do in Calculus 3. As long as you do it the way that I'm going to show you here, all you have to do is find the x, y, and z intercepts, plot them in the 3D coordinate system, connect those points, and then that's pretty much it. And so let me show you what I mean. Remember that intercepts, whether you're talking about a line or a plane, or any other surface for that matter, it's where they cross the x, y, or z axes. All right, so there's going to be 3 intercepts in the 3-dimensional coordinate system. You'll have an x-intercept, a y-intercept, and a z-intercept. And essentially what those intercepts are points where only one of the coordinates are not 0. All right, so x-intercepts are where you just have an x-coordinate of some value, but then the y and z coordinates are 0. A y-intercept is where you have some y-coordinate, but the x and z coordinates are 0. And then a z-intercept is where you have a z coordinate equal to some value, but then the x and y coordinates are 0. All right, and so in order to find those intercepts, all you have to do is set the other 2 variables equal to 0 in your equation, and then solve for the variable that you didn't set equal to 0. So for example, if we want to find the x-intercept, what we do in this equation is set y and z equal to 0 and solve for x. And so if you did that, 12y would become 0 and 6z would become 0, and so you would just have an equation of 5x equal to 60. And so to solve for x, you would just divide both sides by 5, and you would find that x is equal to 12, right? 60 divided by 5 is 12. And so for the x-intercept, we have 5x equal to 60, which gives us x equals 12. And so at x equals 12, this plane that we want to sketch will cut through the x-axis. So I'm just going to say that this right here is x equals 12, which means that if we put a point right there, that would be the point 12, 0, 0. That is the x-intercept for our plane. And now let's see if we can find the y-intercept and z-intercept as well. If we want to find the y-intercept, we want to set both x and z equal to 0 and solve for y. So if we do that, this term will become 0 because anything times 0 is 0. And the same will happen for this term, and so we'll just have 12y equal to 60. All right, so 12y equal to 60 will then give us that y equals 5, because 60 divided by 12 is 5. And so if we go to our 3D coordinate system here, at y equals 5, we have a y-intercept, which would be the point 0, 5, 0. And then finally, we want to find the z-intercept, and so what we'll do is we'll set x and y equal to 0 and solve for z. And so if we do that, this term will become 0, this term will become 0, and we'll have 6z equal to 60. And so if we solve for z, we'll have 6z equal to 60, and that will give us that z is equal to 10. All right, 60 divided by 6 is 10, and so z equals 10 will be the value of z where our plane cuts through the z-axis. That will be the z-intercept. So if this is z equals 10, then there will be a point right there, and that will be the point 0, 0, 10. And now there's only one thing left to do to finish the sketch of this plane, and that is to connect these 3 intercepts. All right, and so if we do that here, that'll look something like this. We connect those 3 points and then shade in that shape, and we get the graph of this plane. All right, now I know it looks like a triangle here. The plane is not a triangle. It does extend forever in 3D space, but this is how we sketch the graph of the plane such that we can see where it cuts through each axis. And that is the most helpful way to sketch it. Okay, so remember, even though we're sketching them this way, where they look like triangles, they're not triangles. Planes are flat surfaces that extend forever within the 3D coordinate system. All right, so for our last example, we want to sketch another plane. We want to sketch a graph of this plane and label any intercepts. This time we have 2x minus y plus 3z equals 4. And let's just go through that same process we did in the last example. We want to find the x, y, and z intercepts. Let's start with the x. If we want to find the x-intercept, we just have to divide the coefficient of x into the value that the equation is equal to, right? Because if we're going to find the x-intercept, we'll set y and z equal to 0. And so those two terms just become 0, and we have 2x equal to 4. All right, and so to solve for x, you would just divide both sides by 2, and that will give you that x equals 2. So the x-intercept will be at the value of 2, and so I'll put a point right there. That is the point 2, 0, 0. And then let's find our y-intercept. So we'll set x and z equal to 0. If we do that, we're just going to end up dividing 4 by negative 1 because we have negative y equal to 4, right? Negative y is equal to 4, which means that y equals negative 4. So negative 4 is the y-intercept. So we're going to be going in the negative y direction here. I'm going to say that right about here is y equals negative 4. And so this point right here would be the y-intercept of 0, negative 4, 0. And then finally, let's find the z-intercept. Let's look at our equation again. This time we're going to set x and y equal to 0. So we'll cross out those two terms because they become 0. And we're left with 3z equal to 4. So we want to divide both sides by 3 to solve for z. All right, so we have 3z equal to 4, which means that z equals 4/3. Which is a little bit bigger than 1. All right, so I'm going to say that that's right about here. That will be z equals 4/3, or the point 0, 0, 4/3, if we plot a point right there. And so that's it, right? We have now plotted all three intercepts for this plane. We have the x-intercept, y-intercept, and z-intercept. Now all we have to do to finish the sketch of this plane is connect those 3 points. And so that will look something like this, okay? And remember to shade it in. That helps you to sort of visualize the fact that you sketched a plane. Okay? And so that's it for this plane. We have now sketched the graph of it. And this was also the last example for this video. But if you do want to see some more examples, I do have a couple more available on my membership site. So if that's something that interests you, feel free to look into becoming a member. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.